Buenos dias. Today we will be talking about partial derivatives. But before we discuss partial derivatives, we should review a few quick things about ordinary derivatives, the sort of stuff that you learned in Calculus 1. Back in your first calculus class, you thought a lot about pictures like this, where you had a function of one variable, y is a function of x, and at some point in the domain, x sub 0, you look at the rate of change of the function, right, which geometrically corresponds to its slope. And the most important geometric insight from differential calculus was that on a local scale, on an infinitesimal scale, every curve looks like a straight line. So if we were to take this little infinitesimal neighborhood and magnify it, my graph would actually look like a straight line. And straight lines are things we're very comfortable with. We know that they have well-defined slopes. And so on this one, it looks like if I go over one little infinitesimal unit, I'm going to go up only 70% as much in the y direction. We would say that in that case, dy dx is going to be 0.7 at x equals x naught. And even if we're not thinking graphically, we can always recognize this derivative as a rate of change, or a local magnifier, as I described it a couple of lectures ago. And we might write something like this. dy dx at x naught, at any given point in the domain, is a rate of change, meaning that it measures in an infinitesimal neighborhood of x naught the number of units by which the function's value rises for each unit by which its input increases. So far so good, and this is all review, and you might think, okay, well now we just need to generalize this into the case of functions like this one, where we have a function of two variables. Z is a function of x and y. And you might think, well, okay, we look at a typical point in the domain like this, x naught, y naught, just like over here. In the one-dimensional case, we looked at a typical point x naught, and then we said, well, above that, locally, curves are straight, and that's what allowed us to think about slope and so on and so forth. What would the analog be over here? Locally, surfaces are going to be like planes. If you go out into eastern Washington somewhere, it looks like a plane, even though you're standing on the surface of a sphere. That's why we call them the planes. So I could imagine drawing in at least a little piece of the tangent plane. And once again, the key idea is that locally, on an infinitesimal scale, if you were a little infinitesimal bug living on this surface, you wouldn't be able to tell the difference between the surface itself and this plane. Well, that's a good start, because planes are, of course, much simpler than general surfaces. They're not curved the way surfaces are, just like over here in the one-dimensional case. Lines are much simpler than curves because they're not curved. But there's an extra twist. In the one-dimensional case, we have lines, and lines have definite slopes, definite well-defined slopes. Over here, however, a plane does not have a single well-defined slope. To see this, think about a box, say the room you are sitting in right now, which is probably roughly shaped like a rectangular box. If I were to draw in the plane that passes through two opposite edges on that box and asked you what is the slope of that plane, you wouldn't be able to answer it, because if I start at some particular point, let's say right here, any notion of slope would depend on which direction I'm moving in. I could walk in this direction, in which case the height of the plane wouldn't be changing at all. So I might say the slope is 0. On the other hand, I might walk in this direction, in which case the height of the plane is changing very rapidly. Or I might walk, say, in this direction, in which case it is changing but more slowly. We don't have this problem with the sorts of functions we looked at in Calculus 1, because there's only one direction in which you can walk from any given point. I mean, you can go forward or you can go backward, but that's it. It's one-dimensional domain. Whereas here, I've got two dimensions in which I can roam around. And it is this problem that leads us to the notion of a partial derivative. The idea of a partial derivative is we are looking at the rate of change of the function, the surface, which can be locally approximated by a plane, when we move our input point in some specific direction. We have to specify the direction we're moving in. And in fact, when we're talking about partial derivatives, we always talk about moving parallel to one of the axes. So it would either be in this direction, in the increasing y direction, or in this direction, in the increasing x direction. We can take derivatives in other directions as well, but those have special names. Those are called directional derivatives. We'll talk about those more in a coming lecture. For now, we're just going to talk about what happens when we move parallel to the y-axis or parallel to the x-axis. And so this idea will lead us to our new definition. We are going to define what is known as the partial derivative of f with respect to x. We will also have a partial derivative of f with respect to y. You might assume that in analogy with the calculus 1 case, where we had dy dx, we would say something like, maybe the partial with respect to x will be dz dx, and the partial with respect to y would be dz dy. And that is almost correct, except we make a tiny little notational change, which is this. We're going to denote the partial derivative with respect to x as dz dx, but we use these funny little curly d's right there. Instead of the usual lowercase d, we have put this little curl on there. It doesn't really mean anything different. It's just a signal to us that we are talking about a function of several variables, and we are taking the partial with respect to one of them, in this case, with respect to x. Anyway, once again, in analogy with what happens over here, dz dx, which we sometimes say partial of z with respect to x, is a rate of change. It's a very specific rate of change, but it's still just a rate of change. It measures, once again, in an infinitesimal neighborhood of the point where we're taking the derivative, same old story as it was in the one-dimensional case, the number of units by which the function's value rises for each unit by which its input runs in the positive x direction. Very important that we're specifying one particular direction in which the input changes. Let's make this a little more concrete by playing around with the picture I've already drawn here. Is it possible for us, just by eyeballing this picture here, to get any information whatsoever about the partial of z with respect to x at this point, x0, y0? Well, we can say that at x0, y0, dz dx, well, what can we say? We have to think about the definition of this thing. dz dx is all about changes to this function when we increase the input value in the positive x direction. So specifically moving along this line parallel to the x-axis. If we're thinking about the partial at a point, we're just thinking about what happens if we restrict this function. Forget about its whole domain. We just restrict this function to one particular line in the domain. Just this one, just the point where we start, and then moving parallel to the positive x-axis. And if we're thinking about that, so if we basically forget the rest of the domain of this function, if we thought about what the graph of the function looked like when we restricted it to just this little slice of the domain, well, we would get things like you put in x0, y0, and you get this point out. You put in this point, whatever that is, and you get some point over here. You put in a point back here, and you get some point over here, wherever it may be. Anyway, you put in all those points, and what would you get? You would get some kind of a curve through the surface. You'd get some cross-section of the surface. For the sake of argument, let's just say it looks like this. All the points on this line, we map them with the function f, and they go, of course, somewhere directly above where they are, and they trace out a curve, something like that. Okay, now what can we say about this partial of z with respect to x at that particular point? Well, what does the partial do? It measures, in an infinitesimal neighborhood, the number of units by which the function's value rises for each unit by which its input runs in this particular direction. So let's imagine what's going on. When we restrict our attention in the domain to this green line, well, the graph of the function gets reduced to just this curve in space. And of course we know that locally, curves look like straight lines. Aha! And now this notion of a rate of change makes perfect sense because we're back to linear functions. We're back down to algebra 1. So if we look in this case, it's a little hard to give any kind of even vaguely precise numerical estimate, but what it does look like is that as we move this point along the positive x direction, what happens to the value of the function? It seems to be going down. So how much does it drop by? Maybe if we move 1 unit in this direction, this would fall by half a unit, or who knows, it's a little hard to guess from this picture. But one thing we could definitely say is that at this point, the derivative of z with respect to x is certainly less than 0. It's negative because the value of the function is falling as we increase the input in this particular direction, in the positive x direction. For the sake of definiteness, let's just make up a value. Let's say that it is about minus, let's say, 0.5. And to play with this numerically a little more, let's remove this general point x0, y0, and let's replace it by something definite like 2, 5. We've gone 2 this direction and 5 that direction. And then this point up here, let's say that is 2, 5, 7. Now, given these three pieces of information, we have a particular point in the plane, we have its image under this map F, it sends 2, 5 to 7, and we know the partial of z with respect to x there. So we could use this idea of a derivative, this general idea of a derivative as a local multiplier, to make an approximation like this. If I wanted an approximate value for f of 2.0025, I obtained that by taking this point and just nudging it a tiny, tiny bit in the x direction. Now, that's more than an infinitesimal, of course, but it's very small, and we know that when we have very small real numbers, then we still get a good approximation to what happens on an infinitesimal scale. Well, if you remember how this works, that is going to be f of 2, 5, the value of the function right there at 2, 5, plus some little bit of change. And that change is going to depend on two things. The amount by which we've nudged this forward, and that amount is going to be 0.002, but we're going to have this multiplier here. That multiplier is going to be our partial derivative, which at the point in question we've seen is negative half. Now f of 2, 5, we've already said is going to be 7, and this extra bit there looks like after we have that, we'll be subtracting off 0.001, and so we get 6.999 is our approximation for f of 2.0025. Good. And so once again, you see how the derivative works as this local multiplier. I know the value of the function at 2, 5. If I move it just a little bit, I take that little bit of change, but for every little bit of change, I have to multiply by some particular factor, namely the derivative, which tells me how this thing is going to change, at least in this particular direction. And that gives me an approximation to the actual value, 6.999. Excellent. Now, I'm not going to rewrite a whole nother definition for the partial with respect to y, but you can imagine how it works. In fact, all I would have to do is change a couple of things here. If I wanted the partial with respect to y, well, instead of dz dx, I would end up writing dz dy. It's still, of course, a rate of change. It measures in an infinitesimal neighborhood the number of units by which the function's value rises for each unit by which its input runs in the positive, not the x direction, but instead the positive y direction. So looking at our graph again, the idea is we would be starting at 2, 5 and moving in this positive y direction. I'll draw the whole line in there. And we would want to know how the value of this function, which right here was 7, how does it change in response to little changes in the input in the positive y direction? And geometrically, once again, we could see what's going on quite easily. When we restrict our domain to this purple line, then the graph gets restricted from the whole surface to a particular curve. All the points on that particular purple line get mapped to. Maybe it looks something like this. If that's the case, what could we say about dz dy? I'll write something in over here. dz dy at that same point, what could we say about it? Well, first of all, it looks like it's going to be positive, because when we move in the positive y direction, it looks like the value along this curve, which is on the surface, is going up very slightly, maybe not quite as sharply as this one is going down, but it is going up. So let's just make something up. Let's say it's going to be about 0.2. And we could use this information right here to make an approximation very similar to what we saw right there. Like maybe we could approximate f of 2, 5.002. So we have moved down this path by this tiny little bit of 0.002. We know the approximate value should be close to 7, since that's what 2, 5 gets mapped to, but we want a better approximation than that. And using our idea of the derivative as a local multiplier, in this case the partial derivative, we have that f of 2, 5.002 is going to be close to f of 2, 5, but we've increased the input. We've moved it by 0.002 in the y direction, and for each unit we move in the y direction, we have to multiply by this partial derivative, this local multiplier, 0.2. And when we do the arithmetic, this becomes 7, this becomes 0.0004, and so the whole thing becomes 7.0004 is our approximation. So now we know that when we move in the x direction, the value drops a little bit. When we move in the y direction, the value increases a little bit. And you might ask, well, what if I move in some other direction? What if I move in some direction between those two lines? Then we would need what is called a directional derivative, and we will talk about that very soon, though not in this lecture. Partial derivatives, which are the directional derivatives in these two specific directions, those are by far the most important, because it turns out that if you know those two, you will be able to get all the directional derivatives from them. So that's to come soon. Okay, now you should know what partial derivatives are, but the question is, how do we actually compute partial derivatives? Fortunately, it turns out that computing partial derivatives is very, very easy. For example, suppose we have this function of two variables right here, and suppose that we want to compute the partial of z with respect to x. The process for doing it is easy if we remember what's going on geometrically. We have a function of two variables, and we can think of that as corresponding to a surface in space. And if we're taking the partial with respect to x, the idea is from any given point, x, y, we're going to be moving in the positive x direction. And we want to see, when we move in that direction, what kind of changes we get in the function itself. Well, calculus is all about motion. As you know, it's the study of change. And what's changing in this case is only the x-coordinate of our input value. Y is completely fixed at every point on this line. That means if we go up here to our function, we are only thinking of x as the one variable that is actually varying. Y, as far as we're concerned, as far as the partial derivative is concerned, we can think of as a constant, because as we're moving in this direction parallel to the x-axis, y is in fact constant. So to take the partial of this function with respect to x, all we have to do is literally pretend that y represents a constant and take the derivative like we would any ordinary one variable function, because now we're just thinking of this as a function of x, where y is just playing the role of some particular constant. And we know that when we take the derivative of a function of x, of one variable, we can do it term by term. So when we start here, we take the derivative of the first term with respect to x, and of course that is 3x squared. Now it gets a little more interesting. When we move on to the second term, we're taking the derivative with respect to x. So we're thinking of y as a constant. Now, if y were some specific constant, like if y were 5, then we would know the derivative of this term of 5x squared would just be 10x. If y were -3, then we know the derivative of this would be -6x. If y is just a constant, then the derivative of this would be 2yx, like so. And finally, the last term, sine of y. Now, a rookie mistake here would be to say that the derivative is cosine y. But remember, we're taking the partial with respect to x. So we're thinking of all other independent variables, y in this case, as being constants. Sine of y, when we move along this line, sine of y does not change at all. And we know the derivative of something that doesn't change at all is 0. So what's the derivative of this term? 0. I'm not even going to write it in there. I'll just say that we are done. I'll just put a period. That's about all there is to it. If we wanted, for example, the partial of z with respect to y, we would do the same thing, except now, since we are letting the y value vary while x is held constant, we would think of all of these x's as being constant, and y is the only piece that's varying. So what would the partial of z with respect to y be? Well, the derivative of this first term with respect to y would be 0. What about the derivative of this second term with respect to y? In that case, we're thinking of x as a constant. If this had just been 9y, we know the derivative with respect to y would just be 9. Well, this is just x squared, which would just be a constant times y. So what's the derivative with respect to y? It is just x squared. And finally, the last bit, what is the derivative of sine y with respect to y? Well, that's easy. Now we're back in calculus 1, that's just cosine y, and we have our partial of z with respect to y. The moral of the story here is that computing partial derivatives is totally trivial. Once you've learned how to take derivatives of one variable functions, you already know how to do partial derivatives. You just carry everything over you learned from your calculus 1 class. You just have to remember that when you're taking a partial with respect to some particular variable, then all the other independent variables are treated as constants, because you are only changing in the direction of that one particular variable. Let's do an example with a function of 3 variables for a change. Let's look at this function right here. It's a polynomial in 3 variables. One question you might ask about this function before we take its partial derivatives is, what does the graph of such a thing look like? Well, it's not something you have access to because we have 3 independent variables and 1 dependent variable. Of course, we could think of the output as being some 4th variable, w. So the graph of this equation would be the set of all points in 4-dimensional space, x, y, z, w, that satisfy this relationship. Unless you can see in 4 dimensions, you are not going to see that graph. And this can be a little disconcerting at first, but it's not really that big a deal in many instances. And there are still ways that you can think somewhat intuitively about such a function in an almost graphical manner. In fact, with a function of 3 variables like this one, at least we can think about the domain graphically. Now, the domain in this case would be all of 3-dimensional space, all of R3, because you could put any values of x, y, and z into this whatsoever, and you get some kind of output. It's not like you end up taking the square root of a negative or the logarithm of a negative or anything like that. So one way to think about what this function f is doing is it's taking as its inputs points in 3-dimensional space. Like maybe you stick in this point right here, 2, 3, 4. And at each such point, at each such input to this function, it's going to turn the input into some new number, w. And in fact, we could compute in this case that f of 2, 3, 4 is going to be equal to 48. So you might say, oh, well, now we know how to interpret it graphically. We've got our input point, 2, 3, 4, and now we just have to go off in a 4th spatial dimension, perpendicular to all 3 of these, 48 units, and put the point there at 2, 3, 4, 48 in R4. Well, that is true, but once again, you can't see it, so it's not going to be much use to you. However, you can interpret it in ways that are useful and that you can get your head around pretty easily. One way I like to do it is to imagine the output as representing temperature. So, for example, we have our domain, just ordinary 3-dimensional space that we're used to, and at this particular point, we can imagine that the temperature is 48 degrees. And the idea is that at every point in 3-dimensional space, you could go to a particular point and say, what's the temperature here? Well, you can just stick the coordinates into that function and find out. If you started at any given point and just followed some curve along, the temperature would be changing as you go, according to this particular formula, or whatever formula you're working with. There's nothing special about that one. And if it's a nice continuous function, as it is here, then of course the temperature will be changing continuously as well. And this will work not only in 3-dimensional space, where it's easy at least to think about the domain, but even in 4-dimensional space or 60-dimensional space. If I had a function of 60 variables, I can imagine a point tracing out some curve in 60-dimensional space, and its temperature varies as we go. The output is easy to understand because it's just 1 dimension. Anyway, I bring this all up as a prelude to computing the partial derivatives of this particular function. So if we look at the partial of f with respect to x, we know how to compute that. We just think of this as a function of x. The other 2 independent variables, y and z, are frozen because what we're doing is at any point we start at, we're moving only in the x direction and seeing how, in this case, the temperature changes. As we do that, y doesn't change and z doesn't change, so they are constants as far as the derivative is concerned. So anyway, taking the derivative of this with respect to x, if I think of y and z as constants, so I've got this constant 2yz times x squared. When I take the derivative of that, of course, I'm going to get 4yz times x. So I'll put it in alphabetical order, 4xyz. And similarly, on the next term, if I'm taking the derivative with respect to x, this whole term is a constant, because as I move parallel to the x-axis, y and z are not changing. And the derivative of a constant, of course, is 0, so nothing happens. And my derivative is just 4xyz. Good. Similarly, if we wanted the partial of f with respect to y, we just have to think of y as being the only genuine variable here, and x and z are held constant because now we're moving parallel to the y-axis. When we do that, if y is our only variable here, the derivative of that first term with respect to y is just all that other stuff. That would just be 2x squared z, that constant. And similarly, the second term, if y is our only variable and z is a constant, that would just be minus z squared. Just as if this had been minus 5 times y, the derivative with respect to y would have been minus 5. If it's minus z squared times y, the derivative with respect to y is just minus z squared. And now, of course, since we have 3 independent variables, we could also take the partial with respect to z. And when we do that, we're going to get 2x squared y for the first one and minus 2yz for the second term. So now we've computed all 3 of the partial derivatives of our function. And to interpret this, we might say, okay, well, what's happening at this particular point where we started? Well, at this point, 2, 3, 4, the partial with respect to x is 4 times 2 times 3 times 4, using our formula for the partial with respect to x. And when you put that all together, that spells 96. So what is that telling us? That's telling us that if we start at this point, 2, 3, 4, and we move parallel to the x-axis in an infinitesimal neighborhood, locally, for every little infinitesimal step we take in the positive x direction, the temperature is increasing rapidly. It's increasing 96-fold from what we're doing. Okay, so it's getting very hot very fast in that direction. How about in the other 2 directions we have? Well, at this same point, 2, 3, 4, the partial with respect to y turns out to be 16. So if instead of the x direction, we move in the y direction, the temperature is also increasing, but not nearly as fast. Well, what about if we move in the z direction? What's happening to the temperature as we move away from this point where it was 48 degrees and we go in the z direction? Well, we find that df dz turns out to be 0, meaning that if we move in the positive z direction on an infinitesimal scale, the temperature isn't changing at all. It might be like if we just restrict our attention to that one line, the temperature, it might be, say, at a local maximum there or a local minimum there, bringing us back to Calculus 1 concepts, to which we will return a little later in this course. And if we were to move off at some other direction that is not parallel to any of the 3 axes, we could discuss the directional derivative in that direction as well, but that will require stuff from a coming lecture. And we have our usual interpretation of the derivative as a local multiplier. For example, if we wanted to know, say, what is the value of f of 2.00234. So we've taken a point very close to where we started. We've just moved it a tiny little bit down in the x direction. Well, we know that that is going to be approximately equal to the value of f at 234. And we also know that there's this extra little bit that we have to add on. We have moved down the road by 0.002, but we have to add in, or rather, we have to multiply in our local multiplier, which would be the appropriate derivative. Well, we're moving parallel to the x direction, so the appropriate local multiplier, the appropriate derivative, would be the partial of f with respect to x at this point. And we've already seen that it has this big whopper of a derivative of 96, so I'll throw the 96 in there. And of course, we said that the value of f, the temperature, so to speak, at our original point was 48, and so now we just have to do a little bit of arithmetic, and we end up with 48.192 for our approximation. And in fact, this is a very good approximation, and it shows how small real numbers work as good approximations to infinitesimals if our functions are nice. If you actually compute f of 2.00234, take those numbers and run them through this thing, the exact value of this thing turns out to be 48.192096. So very, very close indeed. All right, so now you know what partial derivatives are, you know how to compute them, and it's time to talk about some notational variants of partial derivatives. You've seen the little curly d already. There are some other common notations for partial derivatives, just as when you learned Calculus 1, you had to learn some different notations for the ordinary derivative. There was the prime notation and the Leibniz notation, and maybe some others you ran into as well. To begin with, if we have something like z is a function of x and y, we've seen already that we can write things like dz dx or dz dy for the partials. But we've also seen, I did this without even commenting on it earlier, that we might write something like, in place of dz dx, we might write df dx, if z is a function f of x and y. Or for that matter, dz dy could of course be written as df dy. That's not going to confuse anybody. The new notation that might catch you off guard, if I didn't mention it though, is this. Sometimes for the partial of a function with respect to x, we would just write the function itself, f, and then just put a little subscript x underneath. And similarly, for the partial with respect to y, we would just write the function itself with a subscript of y underneath. The advantage here is kind of like the advantage you get with the prime notation in Calculus 1. It gives you a good place to put the argument of a function. For example, suppose we have this function of two variables, log of x squared y. If we wanted the partial with respect to x, we could either write df dx, or we could write f sub x of xy. We would still read it as the partial with respect to x. And let's go ahead and compute this one, since it's a little more involved than the ones we've done so far. We're taking a partial with respect to x. That means that y is being held constant. So we could think of this as just like log of some constant times x squared. Well, you know how to do that. That's just going to involve the chain rule. And when we do that, we're going to get 1 over x squared y, but we still have to do the chain rule. We have to take the derivative with respect to x of the stuff on the inside. Well, y is just held constant, so this is going to be 2 times xy. After a little algebra, that becomes 2 over x. So now we could just write something like, so the partial with respect to x at whatever point you like, 542 is going to be 2/5. And it's a much more compact statement than if we had to write out something using the Leibniz notation with something like at 542, df dx is 2/5. We will use the two notations interchangeably, using whichever one is most suitable for the task at hand, just like you did in Calculus 1 with the notations that you met there. So far so simple, but the place this tends to trip people up is when we get into higher order partial derivatives, when we're looking at second derivatives and third derivatives. Just as you did that in Calculus 1, in this context we can talk about second partials, third partials, that kind of thing. So I need to show you the notation for that and how it works. Let's look at a fairly simple example of a function of two variables. Now we already know how to take the partials of this. Let's go ahead and do that, and I'll use the new notation to get a little practice with that. So if we wanted the partial with respect to x, that would be 4x minus y cubed. And of course the partial with respect to x here, it's a function of these two variables. And now if we were to look at the partial with respect to y, the first term disappears because we're thinking of x as a constant. In the second term, the partial with respect to y would give us minus 3xy squared. Let me try to move this stuff around to organize this better. Okay, the idea is I wanted to set this up so when we move in this direction, we have the partial with respect to x, and when I move in this direction, I have the partial with respect to y. Now let's just look at the partial with respect to x. Well, this itself is a function of two variables. It's a slightly simpler function than the function we started with. As we know, taking derivatives usually gives you a simpler function, and always if we're working with a polynomial like this. So since it's a function of two variables, I can of course take its partial derivatives. And I have two options for how I could do that. I could take its partial with respect to x, or its partial with respect to y. And now I have to show you the notation for that. When we take the partial with respect to x and take its partial with respect to x, the notation is f(xx). Now what do we get in this particular case? Of course we compute it in the usual way. The first term is just going to become 4, and the second term disappears altogether because we are thinking of y as a constant. And I might need a bit more room here, so let me scooch that over to the left a bit. Okay, that's better. Now, suppose instead of taking that second partial with respect to x, we took that second partial with respect to y. If we had done that, several things would happen. The first of which is you would probably hear my neighbor pressure washing his house, but so we'll try to ignore that. If this is awful, I'll just have to re-edit it. Now we know that the derivative of this with respect to y is going to be just minus 3y squared. So I'll write that in, minus 3y squared. But what is the appropriate notation for that? The notation we use for that is f sub xy. We use that order because we have f with respect to x, and then we put a subscript on that. So it's f with respect to x, then with respect to y. Okay, let's move over to this function now, our partial with respect to y, and we'll do the same thing we did over there that we did to that first partial. If we start with the partial with respect to y and take the second partial with respect to y, well, of course, we're going to denote that f(y)y, and the result is going to be minus 6xy. Now for the more interesting one, if we take the partial with respect to y and take its partial with respect to x, so we're getting one of these mixed partial derivatives like we had over here. What mixed partial derivative do we get over here? Well, first the notation. We're going to get fyx in that particular order because, once again, we've got the partial with respect to y, and then we put this subscript x next to it because we're taking the partial with respect to y and then differentiating that with respect to x. And when we do that, we're differentiating with respect to x, so we're thinking of y as a constant, so this is just a linear function, so we're going to get minus 3y squared. And notice something interesting right here. The two mixed partials actually turned out to be equal. So you might ask, is this just a coincidence? It's not. It turns out that the mixed partial derivatives will always be equal to one another, as long as you have a reasonably nice function that you're starting with, and all the functions we will be dealing with in this class are nice, then you will always end up with equal mixed second partial order derivatives. So you now know the notation associated with second order partials in this particular version, but I haven't showed you the notation for higher order derivatives using the Leibniz notation, which is a little weird. Let's start up here at the second row, the things we already know how to deal with. Of course, the first partial with respect to x, we could rewrite as df dx, and similarly on the other side, we get df dy. It's the second order ones that are going to be a little strange. Though, as you hopefully recall, the higher order derivatives in Leibniz notation are strange even with single variable functions. Anyway, when we have df dx, and we take the partial with respect to x of that, we write it in this somewhat ghastly form. Ugh, what does that mean? Why do we use that weird notation? The intuition behind it is that we started with df dx, and then we took the partial of that with respect to x, and so by this kind of nasty abuse of notation, we would write the top like that and the bottom like that. It's ugly. I've never liked this notation. Leibniz is usually very good with this notation. I'm not positive that he's responsible for this, but he may be. If so, well, even the best make mistakes sometimes, but I don't have a proposal for a better one. And this would explain why we have dueling notations throughout calculus. Sometimes they're better in one form than they are in another. Anyway, by the same sort of logic, taking the partial with respect to x and then taking the partial of that with respect to y would look like this. Notice that it is reversed from what we saw before. Here the y comes first, it's on the left. But again, if you think about where this comes from, it makes a certain amount of sense. We started with the partial with respect to x, and then we took the partial of that with respect to y, which is why we ended up again with this badly abused notation to end up looking like that. Whereas if we did the exact same operations but with that other notation, we start by taking the partial with respect to x, and then we take the partial with respect to y, so we end up like that, where here we have xy and here we had yx. Thank God it turns out that the mixed partials are always equal, as I just explained, so it's not a terrible disaster if you switch the order around, but you should try to keep them straight. And moving right along, partial of f with respect to y and then x, done in Leibniz notation, would be second order partial of f, y, and then x. And as we've hinted already, the second pure partial of y would just be the relatively tame thing like that. So using Leibniz notation, we could express the fact that the mixed partials are equal to one another this way. All right. Now there's one last topic we have to talk about. We're going to apply partial derivatives to the question of finding tangent planes to surfaces. Just like in Calculus 1, you often had a problem, here's a curve, find the equation of a tangent line. Now we're going to have questions like, here's a surface, find the equation of the tangent plane. So we're going to combine what we have learned about partial derivatives with what you learned in earlier lectures about equations of planes to solve this problem. So let's get started. We want to discuss tangent planes to graphs of functions. And I'm emphasizing the fact that these are tangent planes to graphs of functions because later we can talk about tangent planes to surfaces in general. The distinction is important because we can have a perfectly good graph, like this closed blob right here, that is not the graph of a function. This can't be the graph of a function for the fairly obvious reason. What would f of 1, 2 be? Would it be, say, this point right here, or would it be this point? This is not the graph of a function because for one input we have multiple outputs. So that's not what we're talking about here. We're just talking about the graph of a function where for each input we get one output. So we get a nice, simple surface. So let's get that other picture out of the way. It's gone. Now, to state the problem a little more carefully, we have the graph of a function of two variables, z equals f of x and y, and we are given some point on that surface. Now, of course, since this is the graph of a function, we can think about the point that got mapped to it. So let's call that point x sub 0, y sub 0 to be definite. That means that the point we're talking about on the surface would have the coordinates x sub 0, y sub 0, f of x sub 0, y sub 0. And sometimes maybe I will just refer to that as z0 for shorthand. Now we've got a surface here, and we know that any little patch of surface on an infinitesimal scale is indistinguishable from a plane, something that is flat. Get close enough and the curvature becomes impossible to sense. Now we can take that little tiny bit of plane and imagine extending it to a full tangent plane. And the question is, what is the equation of this tangent plane to the graph at this given point? Well, there are different ways we could derive the equation of this tangent plane, and I'm going to use a way that uses maybe a little more firepower than is strictly necessary, but I think it will reinforce some lessons about stuff we haven't talked about for a few lectures. To begin with, we can write down a plane's equation if we know a point on that plane, well, we already have the coordinates of a point on that plane, and if we know a normal vector to that plane. So if we could just find a normal vector to this plane, we'd basically have solved the problem already. So all of our effort is going to go into finding a normal vector to this plane. The trick we'll use to come up with the normal vector is to find two vectors that lie inside of the plane. Once we have two vectors that lie in this plane, if we take their cross product, we will get something that's perpendicular to both and therefore will be perpendicular to that plane. So we've actually reduced the problem now to find two vectors that lie in this plane. So let's get our first vector in the plane. What I'm going to do is start down here at x sub 0, y sub 0, and I'm going to move 1 unit in the positive x direction. When I do that, that point is going to be directly below some new point on the plane. Not this one, it will have moved down the road a little bit. Well, I claim that I could find the coordinates of this vector joining those 2 points pretty easily. The first coordinate should be a piece of cake, because I know that in the x direction, this is 1 unit. I did that by design. I said we're going to move 1 unit in this direction. So the first component is definitely 1. The second component is just as easy. As I move from here to here, and the images of those points change from here to here, I stay in this plane right here on which the y coordinate never changes. So that means as I move from here to here, the y value of this point doesn't change at all, which means that that second component must be 0. So far so easy, but we still have this third component to get, and that is the slightly tricky one. It's actually not tricky at all once you recognize where it comes from, but at first you probably don't see it, though kudos to you if you do. Let's try to think our way through it. That third component represents the amount by which the plane's height changes, because this is the z coordinate, the amount by which the plane's height changes in response to an increase of 1 unit in the x direction. We might even say it represents the rate of change of the plane in that particular direction when we increase the x value. That should ring a bell. The rate at which the plane changes its height in this particular direction agrees with the rate at which the surface changes its height as we move in this direction, at least at that particular point, right? On an infinitesimal scale, there's no distinction between the surface and the plane. But the plane's rate of change is the same forever. It's flat. it doesn't suddenly lurch up somewhere else. So that means if I know its rate of change at that little point, I know its rate of change forever, even when we've moved a full unit down this direction. Well, what is that rate of change? We said it agrees with the rate of change of the surface at that point in the x direction, and we know exactly what that is. The rate at which the surface's height changes in response to changes in the x direction is, of course, its partial derivative with respect to x. So for that third component right there, I can put in f sub x, partial with respect to x, at x0, y0, and I have my vector. Good. Now we just have to do the same thing in the y direction. If I started at my point x0, y0, and increased it by 1 unit in the y direction, I would end up with a new point, which of course is directly underneath some point on the plane. And if I join those two by a vector, I can come up with the components of that vector pretty easily. As I move from this point to this point, there's no change in the x-coordinates. It's the same as whatever it was right there. So the first component is 0. The second component, of course, is 1, because we declared that we moved 1 step in that direction. And what about the third component? Well, by the same logic we used a moment ago, that's going to be the partial with respect to y at our given point, x0, y0. And now that we have these two vectors components, our normal vector, n, is going to be red cross green, and to do that, of course, we will set up the usual mnemonic device, which will look like this. And when we crank it out in the usual way, we will get this vector, as you should definitely take a moment to verify. And now we have enough information to write down the equation of a plane, because we know how to do that given a point on the plane and a normal to the plane. So we are now in a position to deduce that the equation of the tangent plane to the graph of z equals f of x and y at this given point is this expression right here. You should remember how to do this from our lecture on planes in general. Remember how it works. These three pieces, right, these multipliers right there, those are the components of the normal vector we had right here. And then we have just the change in x, the change in y, and the change in z. And it comes out to 0 because we derived this using a important property of the dot product. You might want to review that if it is shaky. Anyway, we can put this into a somewhat tidier form. Let me move it up here and get the scaffolding out of the way. This makes a lot of sense. This isn't the sort of thing you should just memorize with no intuitive feeling for where this comes from. This is supposed to be satisfied by every point on this tangent plane. Well, we begin anchoring ourselves to this point right here, x0, y0, z0. So not surprisingly, what this is telling us is that if we move away from that point, what's the new height going to be? Well, we're going to start at z0, the original height. This is giving us the rate at which x values change, and that's just the distance we've moved in the x direction. And this is giving us the rate at which y values change, and that's giving us the change in the y coordinate. So let me box this up and move it one last time, and we'll do a concrete example. All right, there's our conclusion, and here is our problem. Find the equation of the tangent plane to this surface at this point. We happen to know what this surface looks like because we discussed it in a previous lecture. This is a paraboloid. You can think about those cross sections at different values of z. We would get circles with increasing radius going up. Anyway, it would look like this, but even if we didn't know that, we could still solve this problem. We are interested in the point here, 1, 2, 5. And the tangent plane, whatever that looks like, we want to come up with its equation. We need to know a point on it, which of course we have, but we also need to know these partial derivatives at 1, 2. Well, we can get that quite easily. The partial of this function with respect to x is 2x, and I guess I'm introducing notation here, so I should really indicate that I'm thinking of z as f of x and y, while the partial of f with respect to y is just going to be 2y. Hence, the partial with respect to x evaluated at 1, 2 is going to be 2, whereas the partial of f with respect to y evaluated at 1, 2 will be 4. It's growing a little faster in responses to changes in the y direction. So, by our tangent plane formula, the equation we seek is z equals, well, it's the initial height from which we're starting, which is 5, plus the rate of change in the x direction, 2, so plus 2 times the change in x. So that's going to be x minus our initial x value, 1, plus the rate of change in the y direction, 4, times the change in y, which would be y minus the initial y value of 2. And now I'll just push this stuff around and put it in a nicer form. When I do that, we end up with z is equal to, let's see, we're going to get 2x plus 4y. And for our constants, we're going to get minus 2 minus 8 is minus 10 plus 5, so we're going to get minus 5. And that's it. That's the equation of the plane. And we are done with this lecture. Adios.